It's recording.
All right, guys. So today I'm going to be talking about infinity cosmoi, and well, I'm going to be introducing it from quasi-categories, and we'll see if I can do it justice. So, all right, we're going to start with some quasi-categorical background. So this is just the definition that we had last time. Remember, a simplicial set X is a quasi-category. Whenever we have a map from these inner horns into X, there's a red lift of it here. So this is filling in our composition or higher associativity laws. So we can think of the zero simplices as objects. One simplices like these between two objects as morphisms from A to B. And the horn filling gives us composites so that if we have, for instance, this inclusion into X going to something that looks like this, we can compose it to get some composite H. We don't have unique composites in general, but any two composites are unique up to homotopy, which is good enough. So a homotopy of two maps, like Marty explained in his talk, is a two simplex that looks like this. So we have this degenerate edge here and a filling in that says that these two are equal. So in particular, if X is a category, then its nerve is a quasi-category with unique horn filling, and any quasi-category that emits unique horn fillings is also a category. So if we recall the definition of our n simplex here, this is just the nerve of the category n plus 1, which has objects 1, 2, all the way up to n plus 1. Well, we actually saw them as 0, less than, ... is less than n, but we're just shifting indices and arrows between each of them. So in particular, we're going to write 1 with bold font as the category, which is just a point. 2 is the category delta 1, which is just an arrow. A morphism from 1 picks out an object, and a morphism from 2 picks out a morphism in X, because it's just picking out a 1 simplex by Yoneda. So we can identify a category with its nerve in general, and we're not going to write n for the nerve of the category. We're just going to treat the category as its nerve because they're basically the same. So in particular, we're going to write I to mean the free living isomorphism. So that's going to be the nerve of this category. So you have two objects, you have an isomorphism from one to the other and an inverse such that these compose the identity. So the nerve of this is going to give you a category that has two non-degenerate simplices in each dimension. In particular, it's going to look like F inverse, ... F, or starting with F inverse and then alternating. And then every other simplex is going to be degenerate in these n-dimensional places. So now we're going to define a certain class of maps of simplicial sets. So a map from X to Y of simplicial sets is called an isofibration. If whenever we have the following commutative square here, so we have an inner horn inclusion and something down here filling it in Y, and there's a lift up to X. And we also want them whenever we include this on the final edge of I, for instance, or it can be the initial edge, it doesn't actually matter. And then we take it into Y, and there's a lift up to X. So what this means here, for instance, is that if we have a composite of two morphisms in Y, then there's going to be something in X, some composite, that is going to map down to this composite under F. So it's going to see everything that you can possibly compose, all your higher associativity, all that in Y. And down here, what this says that if we have any object in X that goes down to something in Y, and we have something isomorphic to it in Y, which is what a map from the free living isomorphism means, it's the same as giving the data of an isomorphism, then there's going to be an isomorphism in X, which maps down to this isomorphism in Y, which sort of says that on its essential image, if you're treating this as just pure isomorphisms, X is going to just be surjective on that explicitly. So we're going to denote isofibration by two-headed arrows like this.
So that's like homotopy lifting property?
Yeah, so we have a homotopy lifting here. And we also want to have that it's going to be surjective on like the equivalence classes under isomorphisms. So it's a nice enough map. You can always replace any map by an isofibration up to equivalence. So
Can I ask a question? Is that
yeah, go ahead.
maybe you'll talk about this, but is that the right notion of like weak equivalence of quasi-categories or something? Or am I thinking?
We're going to this is just an isofibration. This is not an equivalence of quasi-categories. This is just a special kind of map. Most maps are going to be like this. If you want an equivalence, we're going to define that in a
Okay.
few. So we have the simplicial set X as a quasi-category if and only if the unique map to a point is an isofibration. Well, this is just because, for instance, we can, if we have this map to a point, saying that we can lift against inner horns is just saying that X is a quasi-category. And if we replace this left side by 1 including into I, then since this is just the terminal category, we can map this up here into the identity arrow on whatever object this picks out. So here's a proposition about these, which we're going to use as a black box because the proof uses marked simplicial sets. So if F maps X to Y is a map of simplicial sets, and P maps A to B is a map of quasi-categories, then if P is an isofibration and F is a monomorphism, the map F, the Leibniz tensor F with P is an isofibration. What this means is this map here under this pullback diagram. So some things you can prove with this is that all these other maps are also isofibrations, just using this property. A lot of this is an exercise, but for one example that we can actually do here without wasting too much time is we're going to take B to be the point 1, and we're going to take A to be itself an A with X to Y in inclusion. Then we can form this pullback diagram here. And under this map here, this is just going to be the same as this arrow here. So this means that whenever X to Y is an inclusion, A to the Y to A to the X is an isofibration. In particular, if we take X to be empty and Y to be whatever, you can take the unique inclusion into this. And then this is going to make A to the Y a quasi-category, because this means that A to the Y to A to the empty, which is equal to the point, is an isofibration, which means that this here is a quasi-category by what we said before. So we're going to call maps of quasi-categories a functor. So a functor F from A to B between quasi-categories is an equivalence if there is a map G from B to A and maps alpha and beta such that these following diagrams commute. So this sort of says that we're taking the data of a homotopy equivalence, or a homotopy from the identity of A to GF using the free-living isomorphism as our unit object. What else this means more categorically is if you have, for instance, over here, we're going to take A to something that looks like itself. And then we're going to use this I to give natural isomorphisms to each object A of A to GF of A, such that relevant diagrams commute, which is precisely the data of a natural isomorphism. So what we're saying here is that we have an inverse equivalence, and then we have natural isomorphisms from the identities of each to that, making the witnessing the equivalence. So it's basically the same as an equivalence of categories. And we're going to denote equivalences by this. So one other class of maps is we're going to have a map F from A to B of simplicial sets. It's going to be called a trivial fibration. If for any commuting square like this, there's a dashed diagonal map making the diagram commute. This del delta n is going to be all n minus ones, simplices, and everything smaller than that, all non-degenerate ones of those, but you're missing the unique non-degenerate n simplex of delta n. So we're going to note trivial fibrations by this. So sort of like a fibration and an isofibration. Now, if you look at the Stacks project, chapter 14, there's going to be a proof that a map A from F, a map F from A to B of simplicial sets is a trivial fibration if and only if, whenever you have a monomorphism X from Y, from X to Y, there's going to be a lift like this, such that if the auto diagram commutes. So it's a lifting property against all monomorphisms. You basically prove this by Zorn lemma and using this boundary to keep going up in order to get a maximal map to get a lift. So we can prove for a map F from A to B of quasi-categories, the following are equivalent. F is a trivial fibration. F is an isofibration and an equivalence. And F is an isofibration and what is called a split fiber homotopy equivalence, which means that there's a map going the other way, G from B to A, which is a retract of F. So it's going to be a section of F. So FG is going to be the identity on B. And there's natural isomorphism from GF to identity A, which composes with F to the identity. So what this means is we're going to have a diagram that looks like this. This is going to be a lift of this. This is going to be a natural isomorphism here, which is going to be a natural isomorphism from GF to the identity on A. And if we take the constant homotopy here, so this is just taking everything here back to A, then apply F. This is the same as applying this homotopy from GF to identity of A and then applying F. All right, so we're going to prove part of this at least. So for 1 implies 2, we're going to see that F is a isofibration when it's a trivial fibration, because isofibration we require lifting against inclusions of inner horns, which is in particular an inclusion, and inclusion into the free living isomorphism. And since trivial fibrations lift against all inclusions, they're going to lift against these two. So it suffices, and since 3 implies 2, because being an isofibration and a split fiber homotopy equivalence, in particular, you're an isofibration and an equivalence. So you can just easily see from that that 3 implies 2. So we're going to prove that 1 implies 3. So we're going to use the monomorphism from the empty set to B and lift against this in order to get a splitting for F such that FG is equal to the identity on B. And in fact, we're going to show that any map that has this property is going to work as an inverse equivalence for F. So once we have that, we're going to form this diagram here, the same one that we had before. And since this here is a monomorphism, which is just including A onto the 2 sides of this, because this is like A times an interval. So in this one, you're including into the domain, and this one you're including into the codomain. You're going to have a lift against this because F is a trivial fibration, and this is a monomorphism. And this is going to give you your split fiber homotopy equivalence. And the proof that 2 implies 1 is rather hard, so we're going to black box for that for now. And then here's another proposition that is very useful. So if F from A to B is an isofibration of quasi-categories, and I from X to Y is a monomorphism of simplicial sets, such that either F is a trivial fibration or I is in a class generated by these monomorphisms here, the inner horn inclusions, and the inclusion into the free living isomorphism, then the map, the Leibniz cotensor, I don't know what to call that, F is a trivial fibration here. So in particular, what you can show with this is A to this from A to delta n is a trivial fibration. Taking, for instance, B is equal to 1 and X to Y, just the inclusion of the inner horn. Now that we have all those classes of maps set up, we can finally define an infinity cosmos. So an infinity cosmos K, this is the same thing as a quasi-categorically enriched category. So it's a simplicity enriched category where every functor space, which we denote by fun AB, is a quasi-category. And we also want K to have a distinguished class of morphisms called isofibrations, which we denote by this. We're not going to require equivalences, and we need these to be closed under composition containing isomorphisms. Same thing as you would see up here. You can see that the isofibrations we had are closed under compositions, since if you have a lifting like this, you can first lift up to here, and then you're going to get a new diagram that looks like this, and then you can lift up to here. So that shows you that those are closed under compositions. And you're going to want K to have a terminal object, small products, pullbacks along isofibrations, inverse limits of countable towers of isofibrations, and you want it to have simplicial cotensors. So we're going to explain a little bit more about what those mean in a second. And we also want some properties from the isofibrations. We want them to be closed under pullbacks, products, inverse limits of towers, and Leibniz cotensors with monomorphisms with simplicial sets. And you also want that taking fun x dash is going to preserve isofibrations. So let's expand on these definitions a little. What does it mean for K to be simplically enriched? So this means that for all A and B and K, we have an object, fun AB star, which is a simplicial set, such that we have distinguished morphisms of simplicial sets. One, this is the terminal object, picking out an identity arrow from the functor category from A to itself. And whenever we have, and we also have a composition law. So we have fun AB, distinguished maps, fun BC to fun AC, such that these are associative. So we put out the associative diagram, such as fun CD, X fun BC, X fun B. We can go switch the associativity here. I don't want to write out this whole diagram, but the point is we can apply the composite here, and then we can compose with what is left, or we can apply the composite here and then compose with what is left, and we're going to get the same answer in the end. And we also want identities to do what they're supposed to, so that if we have this map fun AB, this is going to be isomorphic to the terminal objects times it, which we can take by the identity on B to fun BB, X fun AB. And then we can compose that back to fun AB. And we want this to be the identity. Similarly, we can go on the other side with fun AA. So you can also think of this in terms of a certain simplicial object in the category of categories. So for any n, we're going to start with n equals 0. Well, if we just take n equals 0, then that's the same as taking 1 to all of these, and we're going to recover an ordinary category. We can take just fun AB, 0, the 0 simplices, and this is just going to give us an ordinary category, which we're going to call K0. This is the underlying category of K. So we're going to have as objects all the objects in K, and morphisms are going to be the 0 simplices of this. And more generally, we can also take fun ABN. This in simplicial sets are a certain kind of pre-sheaf category. We're going to have all of these products, and everything we want to do is going to be all computed pointwise. So if we take fun ABN as a hom set from A to B, this is going to give us another category, KN. And the degeneracy and face maps on these categories are going to give you functors. So we're going to get K0 it's going to get something that looks like this. So we're going to get a bunch of simplicial categories, and these are all going to have the same objects, and we're going to have all these functors that are going to be the identity on objects. Let's see if I draw this correctly. So we're going to have all these functors that are going to be our face and degeneracy maps. They're going to be the identity on objects. All of these categories are going to have the same objects. They're just going to have different hom sets. This is the same as to give the data of a simplicity enriched category. So our limits, we also want to satisfy a enriched universal property. So what this means is we can unpack this definition. You can ask that fun a comma bn for some diagram, lim n. We're going to get a unique map from this to fun a lim nb if this is just your underlying limit in the one underlying category k0 of k. So what we want is we just want this map to be an isomorphism. So we want this to satisfy a sort of unique enriched universal property such that it's still a limit in all these higher categories. So what it means to be a simplicial cotensor, which is something else we required in our earlier definition, is that if A is an object in K and X is a simplicial set, we can form the simplicial cotensor called A to the X, which we want to satisfy maps and simplicial sets from X to functors from B to A is isomorphic to functors from B to A to the X. And we want this to be functorial in a way that in a simplically enriched way. So what you can sort of think of this as is if you were thinking in like sets and you want to talk about cotensors and sets. So if you have set from X to set YZ as an example, then this would be isomorphic to set from X times Y to Z, which is isomorphic to set from Y to Z to the X, where Z to the X is equal to set XY, or XZ rather. This is sort of the intuition you can take from it.
Can I ask a question?
Yeah, go ahead.
So on the left, you have maps of simplicial sets. The simplicial sets from X into a fun BA. And on the right, you have fun B into AX. Isn't that thing a simplicial set or?
Yeah, sorry. Both of these are supposed to be simplicial sets. Set here means the self-enriched simplicial set map.
Okay.
So where set XY has n faces as X times delta n to Y. Let me do this.
Yeah, that makes sense.
So that this is the set enriched one. But usually I want to draw the underlying. We're just going to mean the enriched one. All right, so what we can do is, so let's expand about what we require these to have. We require, actually, I think we can just define equivalences at this point. All right, so we didn't add any definition of equivalences to what we required of an infinity cosmos, but we're going to require, we say that a map F maps A to B in an infinity cosmos K is an equivalence if fun X A to fun X B is an equivalence of quasi-categories as defined earlier. For all X and K. So a map F from A to B, I just mean a zero simplex of fun AB, so a vertex of this quasi-category here. Generally, we're going to call objects A in an infinity cosmos infinity categories. And maps F from A to B of infinity categories are called they're called infinity functors, but we're generally just going to say functors because infinity functors is a mouthful. So in particular, we have let's get some examples of infinity cosmoi. So claim the category Q-cat of quasi-categories forms an infinity cosmos. So let's check our conditions. We have to see that it's quasi-categorically enriched. So we have fun from A to B. We're just going to define as the simplicial set B to the A, which is going to be the enriched functor category set from A to B. And we saw earlier that for any simplicial set A, B to the A is a quasi-category. So in particular, this gives quasi-categorical enrichment and simplicial cotensors. Where taking a simplicial cotensor is just taking the quasi-category B to the X for X is simplicial set. Because then you can just check by hand that we have set X to fun AB. Well, this is the same as simplicial sets from X to simplicial sets from A to B, which is just isomorphic to, similar to how you do the set case earlier. We're going to have X times A to B, and then we can just move X to the other side. So we're going to have set from A to set from B to X, X to B. Now these over here are both quasi-categories, so this is just the same as functors from A to B to the X, which is just this. All right, so now we need to check that our class of isofibrations as chosen satisfies the condition. So we have pullbacks in the category of simplicial sets. So you need to check that the pullback of an isofibration is an isofibration. Pullbacks exist, and if we have an isofibration here and A, B, C, these are all quasi-categories. We can take the pullback in simplicial sets. We're going to get BXAC. What we need to check is we need to check that this is still a quasi-category. So since these isofibrations are closed under composition, it suffices to check that this map here is an isofibration. And since we have since we have to check the lifting property, if we have, so I'm going to write X to Y here. X is going to be, this map is either going to be the inclusion of an inner horn or the inclusion of 1 into the free living isomorphism. I'm just going to do both cases at once. So I have this map here and I want to lift this. So I'm going to push this forward over to this. So I'm going to get this, look at the map from X to B and Y to A. I'm going to use the fact that this is a isofibration to lift this up to here. And then I have two maps here that both compose the same to A from Y. So using the pullback property, this is going to give me a map up to here that makes this commute. All right, so we have pullbacks against isofibrations, and the pullback of an isofibration is an isofibration. You can use a similar proof here to show that the pullback of a limit of an inverse tower of isofibrations is an isofibration. And using the same proof where you have this limit, you can map this off by an isofibration to one of the objects. And then that goes by an isofibration to the identity. So this is going to be a quasi-category as well. Now, we already checked that we have these simplicial cotensors and that we can take a monomorphism of simplicial sets and an isofibration and cotensor them together. And we're going to end up with an isofibration before. It was sort of a black box, but my dog wants out. 1 second. So cotensors behave well. We have products. To check that a product of quasi-categories is still a quasi-category, we can take a product I. Well, to give this a map here, let me not use I twice. To check that we have this lift here, since this is a product, we can just transpose this to looking at delta I n to a to the j for all j. And these all have a lift. So these assemble together to give a lift into the product. And you can also check that using basically the same criterion, a product of isofibrations is again an isofibration. So we should be done. And if you want to check that, I'm not going to check that equivalences agree quite yet. I think I'll show that later, but this is going to show you that quasi-category is going to form a perfectly good infinity cosmos. And I think I definitely left off a condition in the original definition. I guess it's subsumed under products being isofibrations, but in particular, you want that the unique functor to the terminal object of K is an isofibration. This is sort of subsumed by the empty product, but I should state it explicitly. So you always want this to be an isofibration in K, which is true for quasi-categories by definition. All right, and now we're going to claim that we have cat, the category of one categories, forms an infinity cosmos. In fact, the structure of an infinity cosmos on this is going to be created by including it into quasi-categories. So in order to prove this, this is a second example. So for any two categories A and B, we need to see that A, or rather for categories A and AI, we need to see that their product is still a category. The nerve is a right adjoint functor, so it commutes with products, so there's no issue with that. And we have, for instance, if we have an isofibration here, and all of these are categories, we need to see that we have unique horn lifting against this pullback, which we can do by just checking this against here. If you have an isofibration between two ordinary categories, it should give you unique horn lifting, since you can always just take down to 1 And then any horn lift for this is also going to be horn lift for 1, and that has to be unique because it's a category. So if you had 2 horn lifts here, then you would get 2 different lifts for C. Sorry, if you had 2 different horn lifts, then you would have 2 different maps into C and into A that give you the same universal property over in B, but the universal property of the pullback, which means you would have 2 different lifts for the map from this into A, and that's not going to happen because this is an isofibration and this is an ordinary category. You can similarly check that ordinary categories are stable under inverse limits of towers of isofibrations. And in order to check the same for cotensors, you need to check that a to the x is still a regular category when a is. And this just follows since a to the x is going to be the same as simplicial sets from x to the nerve of a, which is the same as the categories from the homotopy category of x to a, which is just isomorphic to when you take this back to some, this is as a simplicial set. So as a simplicial set, this just means that this is the same as the nerve of this. So this is just precisely the nerve of a category. So it is a category. And the other properties should all follow from what holds in quasi-categories. I'm not going to prove it, but you can also prove that con using the category of con complexes. So these are quasi-categories that lift against all horns. So delta IN into delta N off to A. For all zeros less than or equal to I is less than or equal to N. The category of con complexes is also an infinity cosmos, and you're going to have the same functor spaces, limits. Basically, it's the same story under the inclusion from con into quasi-categories. This is going to give it the infinity cosmos structure that it has. So if we look at equivalences in an infinity cosmos, right, before I prove that, I think I want to introduce the homotopy 2 category. So given an infinity cosmos K, we can form the homotopy 2 category HK, which has as objects the same objects as in K and as morphisms. We're going to call it H fun from A to B. This is going to be the same as the homotopy category of the functor category from A to B. This is just a quasi-category. We're just taking this to be the homotopy category, and we're defining the composition and identity laws as usual. In fact, this assembles to give a functor from simplicial set enriched categories over to cat enriched categories. This homotopy functor, which admits the right adjoint of just taking the nerve. So this embeds fully faithfully into simplicial set enriched categories. But what's the use of this? Well, let's prove one thing that will make it easier to work with equivalences. For a functor f from A to B in an infinity cosmos K, the following are equivalents. F is an equivalence in K. I dot E, fun xa to fun xb is an equivalence of quasi-categories for all x and k. 2, F is an equivalence in the homotopy 2 category of K, I dot E. There is G from B to A, and 2 cells, so natural isomorphisms. We want these to be invertible as well. So invertible 2 cells. Alpha from G, let's do IDA. IDA to GF. And beta from FG to the identity of B. In condition 3, F is an equivalence internal to K. That is to say, there is a functor G maps B to A in K. And functors making the following diagram commute diagrams in K. So we're going to have A into alpha A to the I, A cotensor with I. We're going to have off to the identity. We're going to go off to A. And this is the evaluation at 0. Or we're going to evaluate at 1. And we're going to go back off to A over by, which way am I going? GF. And the other diagram, this is the same diagram we had earlier for equivalences and quasi-categories, but now we're just saying we can do it internally to K. All right, so let's prove this. So for 1 implies 2, suppose F is an equivalence in K. So this means that fun X dash is going to make X an equivalence of F an equivalence of quasi-categories. So we're going to need a helping claim here. If F maps A, let me not use the same letters. Let me use V maps X to Z is an equivalence of quasi-categories. Then phi from the homotopy category of X, the homotopy category of Z, is an equivalence of categories. Well, why is this the case? If we examine what this means, we can just take an inverse equivalence psi from Z back to X, and then we can take diagrams that admit this as the inverse. I'm only going to do one side because the other side is very similar. And then we can take this to the homotopy category. So the homotopy category of X, we're going to go over by gamma to the homotopy category of X to the I. This is not the same as the homotopy category of X to I, but it factors through it. So we're going to get a unique morphism off to here. And then we can evaluate at 0 to the homotopy category of X and evaluate at 1 to the homotopy category of X, which is going to show that this is an equivalence of categories, because this is just how you define an equivalence of categories in general, plus the other side. So we have fun XA to fun XB is an equivalence of quasi-categories. For all X. So upon passing to homotopy categories into the homotopy 2 category, H fun XA to H fun XB is an equivalence of categories. So now we can play some united games. So in particular, we can take H fun A, post-compose with F, to H fun AB is an equivalence. Actually, let me do with the other way first. So on B. So in particular, we can look at 1B in here, and there's going to be some G as an element of H fun BA, which is going to map under F, FG, to something isomorphic to identity of B. So this is going to give us one side of it. And then we're going to use H fun AA to H fun B, should be AB, is an equivalence of categories. Post composition with F should be lower star. I always screw that up. So post composition with F here is also an equivalence of categories. And back here, we can look at GF. So this is going to go over to FGF. And we're going to have an equivalence here down to F just by taking this natural isomorphism here to the identity of B on the first two guys. And then over here, we're going to have one, the identity of A, which is going to map over to F, and this is going to map over here. And since this is an equivalence of categories, and these are both in the image, this means that it's fully faithful, which means that there's going to exist an isomorphism here that maps down to this, which is precisely going to give the claim that identity of A is isomorphic to GF. So 2 implies 3. We have to show that if we have these two equivalences and an inverse equivalence, then we're going to get internally to K this diagram right here. So in order to show this, what we're going to do is we're going to take some inverse to F, G maps B to A. We're going to take alpha from the free living isomorphism in categories to the homotopy category of A to A, which is going to give you an isomorphism from identity of A to GF. So what we're going to want to do is we're going to want to pull this back up to something in the functor category itself, and then we're going to use some cotensors to get the rest of it. In particular, what we do here is note that objects of this are precisely, rather, morphisms in this are precisely equivalence classes of morphisms up to homotopy. And any an arrow phi from X to Y in a quasi-category, such as this one, is an isomorphism if and only if there exists a lift of this, which should make sense because what you're doing is just providing an inverse for it. You can prove this by showing that I is a push out along outer horn fillings from 2, a sequential push out. and then use this in order to get the lift to the full, like the largest groupoid contained in A, the maximal subgroupoid. I'm not going to prove it right now, so I'm just going to use this as a helper claim here. And what this means is we have this here, which is an isomorphism. So we can take some representative. This is going to give us a map from 2 to fun A to A. And we're going to include into I. And since that was an isomorphism, we're going to get an inclusion up here. In particular, we're going to have that if we can take 1 plus 1 into I, this is going to be the same as going up here by IDA and FG, or GF rather. So using our universal property of the cotensors, maps from this to this are the same as maps from A to the I. And we can also note that with these two including here, including into 1 and including into 0, these are going to invert upon going here. So we're going to have identity 0 because this is contravariant in these, in the simplicial sets. So we're going to have A to the I, EV0 to A to the 1 is equal to A. That's the identity by our construction. And down here, we're going to have GF and EV1 down to A. And this is going to be our alpha that we just constructed. Similarly, you get the same thing for B by doing the basically exactly the same chase. So now 3 implies 2, or 3 implies 1 rather. Well, what we use here is we have F maps A to B and G maps B to A. So we can take these for any X and we have fun XA to fun XB by F. And we take this back to fun XA by G. And what we're going to note here is fun XA to the I is isomorphic to simplicial sets from I to fun XA, which is just isomorphic to fun XA to the I as a quasi-category. And this is compatible. So our maps from A to the I to A by evaluation at 0 and GF evaluation of 1 to A. This is going to transpose over to fun from X to A into fun from X to A to the I. And we can evaluate at 0 off to just functors from X to A. Or we can evaluate at 1 off to functors from X to A. And here we're going to have G lower star, F lower star. Similarly on the other side for B, which is going to admit that this is an equivalence from fun XA to fun XB, which is what we were trying to show. I think I'll probably stop there for today because we're close to the end on time. If there are any questions, go ahead.
Okay, let's thank Logan. Thank you.